vamos finalmente con el último trabajo. Es un trabajo que se llama Methodology for the Creation of More Realistic Scenarios of Rooftop PVs Allocation in Monte Carlo Studies, que lo va a estar presentando Diego Almeida. Diego Almeida is a master student in University of Campinas. I'm not sure if you understand Spanish or not, but you can give the presentation English, Spanish, whatever you want.
Okay. My name is Diego, and I will introduce you to the paper Methodology for the Creation of More Realistic Scenarios of Rooftop PVs Allocation in Monte Carlo Studios. Well, this topic is very important because in last years, distribution networks have undergone several changes, and one of the main changes is the strong presence of PV systems on the grid. In Brazil, for example, which is the scenario studied in the paper, there are several factors that contributed to this increase. Are they great reduction in the costs of photovoltaic modules, use of incentive mechanisms which aim mainly to reduce environmental impacts? One of these incentives, for example, is net metering, which is basically an electricity energy compensation system where consumers who inject energy into the network are rewarded with energy credits. Another factor that contributes to the increase of PV systems in Brazil is the high solar radiation. And according to surveys carried out, the expectation is that the participation of solar energy in the Brazilian energy matrix will increase ever more, reaching about 10 gigawatts of installed power by the year 2029, double in size compared to the amount accumulated in 2020. The question that is asked then is, are the distribution systems prepared to withstand such a change? This is an important issue, as distribution systems are designed to operate radially, that is to provide power flow in a single direction, from the utility to the consumers, and not to operate in reverse, which is what occurs when there is distributed generated. In the case of consumers unit with distributed generation, they produce their own energy and can inject power into the grid. If it produces more energy than it consumes, there will be a reversal of power flow. And depending on the amount of reverse flow, several problems can occur to the electricity system, which will be discussed on next slide. One minute. The animation now shows the reversal of the power flow, which occurs when there is an increase in distributed generation. Well, the main negative technical impacts of these are overvoltage, reduction of power factor values, mainly in distribution transformers, increased technical losses, transformers and cables overload, voltage imbalance, and protection discoordination. So we have to pay attention to these problems because they generate costs for energy utilities and therefore they must be considered in studies for the planning and operation of distribution systems. The objective then of this work is to develop a methodology to define the most likely scenarios of the distribution networks with rooftop PV systems. The idea is to apply this methodology in real distribution networks and probabilistically evaluate the results of this application to help in the understand and better use of PV systems. The most likely scenarios for solar generation are created from Monte Carlo simulations, use the allocation of PV system as a random variable. Monte Carlo simulations, for example, are widely used to reproduce systems that involve uncertainties, such as the random allocation of PV systems. Therefore, it is an extremely important method for simulating possible scenarios with rooftop PV systems. Methodology for scenario creation. The general idea is to receive a list of all possible PV systems that can be connected to the network and run a series of rules to filter out those with the greatest potential to be installed on the network. The proposed methodology comprises 4 steps. Step 1, reading and filtering of the distribution utilities database. Step 2, size rooftop PV systems. Step 3, selection of local candidates. Step 4, creation of the Monte Carlo scenarios. That figure on this slide shows that the possible PV generation scenarios are created from the analysis of the database of a real electricity utility in Brazil. Querying the database's performance using scripts developed in Python. Step 1, reading and filtering of the distribution utilities database. In the first stage, a careful query is made to the distributors database understood. It's very important information such as, for example, average monthly energy consumption, availability cost, voltage group, identification of the consumer units, and several others are used for this evaluation. In the first stage, the total numbers of consumers registered in the database is around 4,816,000. Of this total, 7.7% of consumers are removed because 1.5% have network connectivity issues and therefore cannot be modeled. 0.36% are medium voltage consumers, which we are not interested. We are only interested in low voltage consumer, and 5.85% are units registered in the database but are disabled. Step 2, size rooftop PV systems. In the second stage, all consumers are assumed to be potential candidates. Therefore, at this moment, the PV systems are dimensioned for each of the remaining consumers for the previous step. The size of systems is given by the equation shown on the slide. This equation here. Some observation in this equation. This calculus is based on net metering. The numerator of this equation basically expresses the energy that you want to produce by the photovoltaic system in 1 year that is sufficient for the consumer's own consumption, discounting the consumption related to the availability cost. And finally, the denominator expresses the solar generation potential in 1 year. Therefore, no consumers is eliminated from the candidate list in the second step. Now, step 3, selection of local candidates. In the third step, the dimensioned systems are filtered based on the previous step in order to make the simulations closer to reality. For this, 10 practical rules described below are applied. Rule 1, elimination of PV systems with a capacity lower than 1 kilowatts peak. The first rule eliminates PV systems with a capacity of less than 1 kilowatt peak, as they were considered economically unfeasible. Therefore, these were removed from the candidate list, which resulted in the elimination of about 1,650,000 55,000 PV systems, corresponding to about 692. Rule 2, selection of PV systems with a capacity between 1 and 1.5 kilowatt peak. The second rule randomly eliminates 50% of consumers with a photovoltaic capacity between 1 and 1.5 kilowatt peak, as they are considered economically unfeasible. The elimination of the numbers of PV systems and megawatt peak is indicated on the slides. These numbers here. Rule 3, saturation of PV systems with a capacity greater than 75 kilowatts peak. The third rule limits the photovoltaic capacity of PV generators to 75 kilowatts peak, since the PV systems considered have a maximum of 75 kilowatts of installed power. This rule does not eliminate PV systems, it only eliminates megawatts peak. Rule 4, removal of PV systems from single-phase consumer units. The fourth rule eliminates single-phase PV systems, since the offer of single-phase inverters in the Brazilian market is small. Rule 5, the fifth rule removes PV systems installed in buildings. This rule was established because, in general, the roof area of buildings is relatively small and may be sufficient to serve all consumers in that building. To remove the systems, it is necessary to access the distributors, GIS. The GIS is the Geographical Information System, and through it is possible to locate all elements of the network. The figure on the right here, for example, shows how the removal is done. The area of complex who formed the ends of the secondary network in question is calculated, as the area of this convex who is now zero and serves more than one consumer. Then it is concluded that these consumers are not part of a building. Otherwise, as shown in the left figure, consumers are part of a building. And Rule 6, saturation of two-phase PV systems at 8 kilowatt peak. Rule number 6 limits the nominal capacity of two-phase PV system to 8 kilowatts peak. This was established because of the high value of two-phase inverters with a capacity greater than 8 kilowatt peak. Rule number 7 limits residential PV systems to 20 kilowatt peak because of the relatively small roof area for installing larger systems. For the rule number 8, the graph shows the distribution of installed power of PV system in relation to consumption class. In this graph, it's possible to see the low adherence of PV system by the consumption classes: all consumption, street lighting, and public service. So it was decided to remove this PV system from the candidate list. Continue. From the Rule 9, due to the low energy consumption, another type of PV installation considered economically unfeasible were where the consumer units associated with activities such as, for example, condominium administration, road lighting, traffic lights, radar, monitoring, cameras, communication, telecommunication service, religious temples, and other business units with activities similar to these. Finally, rule number 10, for the removal of PV systems. Also, due to the low probability of installation rooftop PV systems installed in consumer units associated with stores, box, living room, and apartments were removed from the candidate list. At the end of the stage, there is a removal of about 75% of the rooftop PV systems initially considered suitable for installation, which corresponds to a reduction of about 50% megawatt peak. Step 4, creation of the Monte Carlo scenarios. In the last step, the scenarios for the Monte Carlo simulations are created. For this, 1,000 different scenarios are generated, where each scenario has a given sequence generated randomly. For example, in scenario 1, there is at least one of consumer units. In scenario 2, there is another list, and so on. Furthermore, the scenarios differ by PV penetration level, which is defined as the percentage of installed PV systems in relation to the total of systems that can be installed. This step is optional, and some modifications are made to the scenarios obtained in the previous step. To avoid punctuous concentrations of PV generation, it is necessary to analyze each scenario created in the previous step and identify the moment when the activation of a new PV system results in a violation of the PV penetration limit, defined as 2 times the rotating capacity. Simple put, the rotating capacity is the maximum distributed generation capacity that the feeder can accommodate. Above this limit, the network starts to have serious problems. Illustration of application. From this slide on, an example of the application of the methodology will be shown. But first, it is important to talk about some issues involved in the simulations. Well, the first one is that the electricity grid was modeled on OpenDSS.
Diego, 2 minutes, Diego.
Completely.
Sorry, 2 minutes, yes.
Okay. From this slide on, an example of the application of the methodology will be shown. But first, it's important to talk about some issues involved in the simulations. Well, the first one is that the electricity grid was modeled on OpenDCS, which is an open source software that allows you to perform simulations of distribution networks with distributed generation. Another observation is that the analysis of the results is based on technical losses. In addition, the simulations performed are of the quasi-static time series type. That is, they are series of simulations of power flow in time. Each series of simulations considers a given PV penetration scenario. That is a given group of PV microgenerators and a given PV penetration level. 1,000 different scenarios and 6 penetration level are used. 0%, 10%, 20%, 30%, 40%, 50%. Test system. The test systems used in simulations are real and are 2 electrical sets located in the city of Campinas. One code AETR 101 and the other BETR 103. The ATR 101 electrical set serves 5,768 consumers units, where 2,870 consumer units are able to receive rooftop PV systems, while the BITR 103 set serves 6,519 consumer units, where 1,856 are able to receive rooftop PV systems. In this graph, the distribution of total losses in box plots is presented. The green line within each box represents the median and can be used to visualize the behavior of total losses. It's possible to observe, for example, that for the AETR 101 circuit on the left, the total losses decrease with decrease of the photovoltaic penetration until reaching the PV penetration level of about 20%. At this point, the system is on the brink of power reversal. What do I mean by that? That at this point, most PV systems are producing the energy necessary to supply the all load, which reduces current circulation in the grid and next energy losses. We can see that from the PV penetration of 20%, the total losses change behavior, increasing significantly with increasing photovoltaic penetration. As for the circuit BETR 103 on the right, there is different behavior where the total losses decrease as the PV penetration level increases, which shows that each network has its own characteristics that define the point of imminence of the reversal of power flow. In conclusion, the proposed methodology seeks to create scenarios closer to reality regarding the installation of photovoltaic systems in distribution systems, where each scenario considers a certain sequence of consumers capable of installing PV systems. For this, the distributors database understood was carefully analyzed so that the appropriate dimensioning and elimination of those photovoltaic systems with less potential for installation could be carried out. And thus the set of scenarios can be used to carry out probabilistic analysis of the technical impacts caused by the insertion of PV systems into the network through various computer simulations. Therefore, the present methodology proves to be important to guide decision-making by energy utilities. Thanks. That's all. Thank you very much.
Thank you, Diego. If there are any questions, please put them in the question and answer. We are a bit late, but if we have time for one question. In the meantime, while I'm waiting for question, I want to thank Daniel, Roberto, Alfredo, and Diego for all the presentations. Thank you very much, and everybody that all the attendees that were listening. So, thank you all, and thank you for that's the end of this session. Thank you very much.
Thank you too.